Hi. Before the title of this video scares you off, let me tell you what this video mainly will be about. It's about using bit patterns, that means sequences of bits, in order to represent so-called unsigned integers. Unsigned integers are integers where a value can only be non-negative, so 0 or larger than 0. And also, these bit patterns will have a fixed amount of bits. For example, 4 bits or 8 bits, but in general, n bits. Now, another thing will be that in upcoming videos, I will also show you that bit patterns can be used to represent also signed integers, for example, where a value also can be negative, or to represent floating point numbers, where we have values like 1.25, or to represent characters, or to represent machine instructions. So it might be already kind of clear that by just looking at a certain bit pattern, it's by itself not clear what this bit pattern is supposed to mean. So we, for example, have to come up with a notation which gives a certain bit pattern an additional context so that we can see, okay, in this context, it is representing an unsigned integer, like in this video. And we also have to come up with some definition, which is actually mapping what we see to its meaning, the bit pattern to the value that it represents. And something similar you already dealt with in connection with numbers, and I will take advantage of that you learned what is the meaning of a number and how can we write it down with a numeral representation in some symbolic form. So let's take advantage of that, and let's first recall what you already know about that. In school, you got a kind of intuitive introduction to numbers. You first learned to count, and by that you got an understanding about the meaning of natural numbers. You learned that 1 is a natural number, and that after the 1 you have the 2 and then the 3. So you learned basically that 2 is the successor of 1 and 3 is the successor of 2. You gave these numbers names, but most of all you learned about their property. And then you extended the set of natural numbers to integers, and the set was extended to rational numbers, and the set to real numbers. And at university, you got a much more formal introduction to numbers. Maybe you started with the real numbers and defined them axiomatically as a complete ordered field. And then you defined the rational numbers as a certain subset of that, and the integers as a certain subset of the rational numbers, and the natural numbers as a certain subset of the integers. So it became kind of more clear that first of all you have this mathematical meaning, but of course you still had to write down particular numbers in a certain symbolic way, and the term for that is the numeral that you use to express what number you mean. And for that, we just review a few examples how you can write down a certain, in this example, unsigned integer, the integer 15. And the simplest way to find a numeral representation for that would be just using tally marks. Basically, that's like using fingers. In this case, it's kind of hard to use 15 fingers, but the idea is the same, that you just make a certain amount of marks, and this amount represents the value that it represents. The disadvantage of tally marks is that for large numbers, you have to make many marks. So that's why it's probably just popular in prison, or in particular in prison, because there you have enough time to write down whatever number you have to write down. More convenient, because it's more compact, are the Roman numerals. In this case, you just need 2 symbols. But for actually doing math in school, you learned how to use the decimal notation, the decimal numeral representation. And just recall all these rules that you learned for adding, subtracting, multiplying, dividing integers. Those rules were easy to learn once you got the idea of the meaning of this representation. And we can use this concept that was used for decimal numerals for other representations as well, and the rules that we learned for doing these operations can be carried over. And this, for example, will be useful for this hexadecimal notation, this octal representation, or in our case, in particular, binary representation. Now, let me basically show you how I learned to understand the meaning of a decimal numeral. I was told that if I have a sequence of digits like that, then each digit has a certain weight. For example, here the 4 has the weight 1, the 3 has the weight 10, the 2 has the weight 100, and the 1 had the weight 1000. So of course that required that I already understood the meaning of 1, 10, 100 and 1000, and also the meaning of these digits in general from 0 to 9. And I also had to understand how to do some simple multiplication and addition. But then it's kind of clear that such a sequence can represent this computation. And if this computation is well understood, here on the right-hand side, the thing on the left-hand side is well defined. Now, of course, this is no big surprise to you. That's probably how you also kind of learned it. Now, let's rewrite this definition in a way where we use this exponential form, where we replace, for example, 1000 with 10 exponent 3. Then you see that these positions can be called differently. Instead of O for ones, I call this position, for example, 0, and the other positions 1, 2, and 3. And then you see from this position, we get the exponent of the associated weight. And this now can be easily be generalized. What we in general have are a certain amount of digits, in this case 10 digits from 0 to 9. We just need 10 different symbols for each of these digits, and we have to understand the meaning of each of these digits. And we have to understand the meaning of the base, the exponents that we need, and how to map the position of a digit to this weight. So this example easily can be generalized. First of all, we use placeholders for this single digits, and these placeholders have an index, and the index just gives us the position of this digit, like before. And then by looking at a general 4-digit sequence of decimal numerals, we know its meaning is defined by this mathematical computation. Now, if we are also dealing with other numeral representations where we have a base different from 10, we somehow need to point out what base are we actually meaning. And in this case, we could point it out like that this is a sequence of decimal digits by putting this digits within parentheses and also use this 10 as an index. And then also sometimes it might be required that we need to make clear what is a single digit and what is the next digit. So we also could use commatas in order to separate them from each other. No big deal. And then also maybe we want to point out that this is a numeral that represents a non-negative integer, unsigned integer. And we can therefore agree on a notation like that, where we have this u of certain sequence of digits with base 10. And the next step, of course, would be to generalize this to n digits, and that's easy. We just then have a sum defining this numeral from 0 to n minus 1. We also need to think about what range of values can we actually represent. And let's go back to the example where we have 4 digits. Then the smallest number that we can represent would be 0. And the largest would be 10,000 minus 1. Because the largest number would be having the digits 9, 9, 9, 9. And the next would be 10,000 or 10 exponent 4. So we have a range from 0 to 10 exponent 4, one less, because 10 exponent 4 is the first number that we cannot represent anymore. And in general, we would have a range from 0 to 10 exponent n minus 1. Okay, and now all we have to do in order to generalize this to an arbitrary base larger than 1 would be to replace the 10 here with b. So in a special case where b equals 2, we have a binary numeral representation, and let's say we have 4 bits, then the meaning of a 4-bit pattern, when we want to map it to an unsigned integer, would be defined by that, where we have values from 0 to 15. The largest value would be 2 exponent 4, that's 16, minus 1, that's 15. Let's also use this example to introduce a few definitions, a few terms. I was already using the term bit for binary digit. Other terms that we often will use are least significant bit and most significant bit. And this is about the position of a certain bit and what weight it is associated with. So for example, the least significant bit is associated with the weight 1 and the most significant bit, in this case, with the weight 2 exponent 3, or in general with the weight 2 exponent n minus 1. Another base that we frequently will use is the base 16 for hexadecimal numerals. And there we have 16 digits with values from 0 to 15. So we have to either use a notation where we separate digits from each other with commatas, if we want to use decimal numerals for representing hexadecimal digits, or we agree on symbols that represent these values from 0 to 15. And the common way to do that is to use the digits, the decimal digits from 0 to 9 for the values from 0 to 9, and the characters A to F for the values from 10 to 15. And whether you are using uppercase characters or lowercase characters doesn't matter. Both is common. Another thing is, if we write down a hexadecimal numeral, we in general have to specify that this is a numeral to base 16. So we could use this notation where we put it within parentheses and use the index 16. But because we use hexadecimal numerals so often, we need a more convenient notation. So the special case needs special treatment. So 1b would be an example where actually it's maybe from the context clear that it's probably representing a hexadecimal, but think about the numeral with digits 1, 2, then it's not clear whether it's a decimal numeral or a hexadecimal numeral. And here we use a common convention that prefix OX indicates that remaining digits are hexadecimal digits. So we would write it, for example, like that. And if we want to point out that this is actually representing an unsigned integers, then as before, we would put this hexadecimal numeral within this U of notation. And then the mapping is clear. The reason why hexadecimal numerals will be so important for us and frequently used is because bit patterns that we will deal with usually have multiple of 4 bits. For example, 4 bits, 8 bits, 16 bits, 32 bits, or 64 bits. Those will be the most frequently used bit patterns. And then we can use hex digits to write them down in a more compact form. With one hex digit, you can represent a bit pattern with 4 bits. And the mapping that I show you here with a 4-bit bit pattern mapped to a hex digit is done in a way so that the left-hand side, where we have a bit pattern, has the same unsigned value associated to it as the unsigned value of this hex digit. And I will show you this mapping actually in Circuitverse, where I will connect a 4-bit input with a hex display. And we'll see that that's exactly what you see in Circuitverse. And I also will show you how you can then represent the 8-bit pattern with 2 hex digits. And this is done by grouping this bit pattern into groups of 4 bits, like that. And then each group can be represented with 1 hex digit. So in this case, the first group with the hex digit 3 and the second group with the hex digit F. And also here, if you have a group with 8 bits or any amount of bits, the unsigned value gets preserved. So the unsigned value of the bit pattern equals the unsigned value of the hex numeral. Let's begin with a 4-bit input device. What we do is, like in the last session, we first pick from the circuit elements an input device. Now this is a 1-bit bit pattern, and then here at the property box we can increase the bit width to 4, and then we have a 4-bit wide bit pattern. And then we could just connect it with a 4-bit output device, and we also would increase just the bit width to 4. And if we now connect this with a strip line, then you actually have here not just one wire, you actually have here 8 wires, but represented as 1 wire. So it's a bunch of wires. But what we also can do is we can use a different output device. You can select here the hex display. And then you just can connect this here as well with the input device. And now we see the bit pattern with only zeros would be represented as hex 0, and then you can check whether this mapping that I showed you on the slides is actually working. And for example, a bit pattern with only ones would be mapped to F. One important thing that I should point out is if we look at the bit pattern that is mapped to B, you see here a symbol with a lowercase b. The F was uppercase, and the reason why the B is in lowercase and other letters in uppercase is the uppercase B displayed in a hex display would just look like an 8, and you don't want to mix it up. But important is that this here is not a 6. The 6 would be displayed like that. So this bar here is important, and in the past this was sometimes causing confusion. Now, how can we display the bit pattern with 8 bits with 2 hex displays? Let's just move this up a bit. Then I go back to the input devices and I will create an 8-bit input field. And now if I would just connect here an output device, a hex display to it, you would get an error because the hex display expects 8 lines, 8 line straps. Now what I have to do is I first have to split this wires into groups of 4, and let's move this here away. For that I can use a so-called splitter, that's this symbol here, and here I have to enter the bit width. That means the total number of wires that we basically have. In this case this would be 8, and I want to split it into groups of 4. And then I click here on OK, and then I enter here 4 space 4, and then this 8 wires are split into 2 blocks of wires, where each block has actually 4 wires internally. Now you also see here from the notation this basically gives you the position to which bits it's connected. And so for example here 0 to 3 means it's connected to this, 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 and this bit with the positions from 0 to 3. And then I can connect this hex display here with this 4 wires and a second hex display with the other group of 4 bits, like that. And you can see here, if I'm changing this value, let's put that back to 0. If I'm changing here this value, it's flipping from 0 to 1. And now I would get here an F for this group of 4 bits. And then here this group could be changed to a bit pattern with hex digit 1. And basically that's what I showed you on the slides before. Mainly for completeness, because we will not use it in this lecture at least very often, I also want to mention octal numerals and what kind of typical conventions and notations are used. First of all, for the digits, we don't have to agree on special symbols to represent them, because we only need 8 digits, and therefore we just can use the decimal digits from 0 to 7. For writing down an octal numeral and avoiding this notation where we put it within parentheses and specify explicitly the base 8, the convention usually is that an octal numeral begins with a leading 0. That means if you see a sequence of digits like 0, 1, 7, then it's representing the octal numeral with digits 1 and 7. And the actual unsigned value would then in decimal notation be 15. The reason why sometimes octal numeral can be of advantage is that with one octal digit you can represent 3 bits. But in our cases, the number of bits is, as I said before, usually a multiple of 4. So we will usually not take advantage of that. In upcoming videos, I will show you how circuit words can be used for adding numbers, and there we will take advantage of the fact that we already know how to do such operations in a decimal representation. But for this video, I want to finish with this table that you also find on the website, where you have a quick way to look up the mapping from bit patterns to decimal, hexadecimal, and octal numerals.